So being done 3.4, and if you remember, we already did 3.5 previous to that. We're now in 3.6, which is optimization problems. And we've got 2 different lessons that we'll do on that. So we're going to be solving for word problems where the equation is not given to us and we have to come up with the equation or sometimes equations in order to solve the problem. So what does optimization mean? So that means we're reading the question and we're trying to optimize the situation. So for example, to optimize means to either maximize, my rating tool here. So I'm either maximizing or minimizing. So I either want to maximize or minimize the situation to make it optimal. So just I'm thinking of some examples, like to maximize is usually space, right? So let's say you have an open backyard or kind of out, your backyard can be part of a field and you want to fence it off. You want to create the maximum area of that space, right? With the same, let's say, perimeter of fencing. How can you lay that out to have the most space inside? So maximizing, there's things like space. Minimizing, let's say, is usually money. If we're talking about businesses, right? They want to spend the least amount of money creating like for production costs to produce their product, let's say. Or maximizing could also be money on the side of for profit. So for maximizing, you would probably want to maximize your profit, right? What price do I want to choose? For advertising, that's going to create the most profit, where then beyond that, if I spend any more money on advertising, it's just kind of a waste, right? It's already reached its maximum audience and had its most effect. So just kind of talking about what kind of questions would be optimization questions. Trying to make the situation as best as possible by either maximizing again or minimizing. So when we're looking at these questions, the steps we want to follow is, again, part of this would be figuring out what the question is asking. Does it want me to maximize? Does it want me to minimize? What would be the optimal situation there? Define your variables. So you have to figure out, are you going to be using X and Y? Do you have 2 variables? What are they going to be, and defining them, giving a sentence, let X represent whatever that is, let Y represent whatever that statement would be. Draw the diagram if it helps, if you're able to. Identify the quantity that's going to be optimized and then write an equation. So again, depending on what it's asking, what you want to optimize, you're making an equation based on that optimization. If the quantity being optimized is written in terms of 2 variables, then you can't solve for 2 variables, right? Then I need to write up another equation. So this is going back to grade 10. Then in the other equation, I'm going to rearrange one quantity in terms of another. If you just think of then substitute, basically we're using substitution, right? From grade 10. Identify and state any restrictions on the independent variable. So for example, independent could be time, right? Time can't be negative. So that's one type of restriction. Just making sense out of the question. Then we want to differentiate the function. We want to get the first derivative, figure out the critical numbers, and classify them. Now this step here is a bit different than in previous videos. Classify them using the second derivative test, and then answer what the question is, right? So let's just basically start with an example. And just to point out before we start here, I'm not graphing in these questions, right? It's a drawing. I'm coming up with a solution. I'm no longer graphing like I did in the previous lessons. So we won't need to do the first derivative test indicating with the chart, indicating whether I'm increasing or decreasing, because I'm not drawing a graph. So there is parts that we've done before that we're able to skip in this case. And that's why we're moving from the differentiating the first derivative and then into the second derivative test. Okay, let's get started. I have a rectangular vegetable garden and it's going to be built with 60 meters of fencing. So that's how much fencing I can't use any more, any less. The garden is going to be divided into 2 equal parts by another fence parallel to one side. But again, total is still 60 meters of fencing. Determine the dimensions of the garden so that the total area is maximized. So there's our optimization. We want to maximize our area, means one of our equations, or maybe the only equation, is going to be our area equation. So to start, identify what the question is asking. So the question is asking us to maximize the area using only 60 meters of fencing, and we know we have a rectangular garden separated into 2 different spaces, right? Define our variables and do the drawing if it helps. So I'm going to start with the drawing. Basically, we'll do both at the same time. So I could do straight lines, but do a rectangular. Again, if you were to do this freehand in your notes and it looked basically like this, that's good. You know, that's not the best there. It's getting a little bit slanted. And then, so there's our rectangular vegetable garden. The garden is to be divided into 2 equal parts. So if I was to divide it, again, just freehand down the center by another fence, so this is also a fence, parallel to one side. So we're parallel here to the width, let's say. So you could use any variables you want. If you want to use, like I just called this width, right? If you want to call this W for width and call this length, or I'll start with labeling these X. So let's say let X represent the width. The width of the garden, obviously, but I'll just say the width, and that would be in meters, right? Include your units. So then the length is going to be all the way from one side to the other, and all the way from one side to the other. Let Y represent the length in meters as well. Okay. And then for my equation, going into the third bullet there, identify the quantity to be optimized and write the equation. We know that we want to maximize area. So if I say area equals, I could just say, you know, if I'm using the letter A, let A represent the area. And just to go over, area is squared, right? Meters squared. So let's continue. Let's make our equation. So we're talking about maximize area, the whole entire thing being shaded in. So area is length times width. We're talking about the width would be X and the length would be Y. So area, if you take a look here, would still be just X times Y. X times Y would shade in the whole entire thing. But what do you notice here? I'm looking at the 4th bullet. If it's written in terms of 2 variables, then write another equation. So I have 2 variables here. I'm not able to solve if I have 2 variables. So I need another equation. So what is that second equation going to be? I've dealt with area, length times width. If I go back to the question, the other number in the question is the 60. The 60 meters of fencing is dealing with perimeter, right? Could I do an equation dealing with perimeter? So using all of these sides, all of this fencing, so I would have 3 widths, so I would have 3 X's, plus perimeter is adding all the way around, plus 1 entire Y and another entire Y, so plus 2Y would equal 60. And then like it says there, basically the fifth bullet, rearrange one quantity in terms of another and substitute that into the other equation. So I can here isolate for X or I can isolate for Y. Honestly, it doesn't matter, whichever one you want to do. So if I'm going to isolate for Y, I'm going to keep Y over on the left-hand side, throw that 3X over. So negative 3X plus 60, divide by 2, negative 3/2 X plus divide by 2, half of 60 would be 30. And if I wanted to, I could change that into negative 1.5. You can make that a decimal instead of a fraction. So there's my equation. And I'm going to sub this into equation 1, right? Going back and reviewing substitution here. Rewrite number 1 is area equals length times width. I have a value for Y, so that equals X, and then instead of Y, I'm putting negative 1.5 X plus 30. And then just double check that that's right. I have my X and I have what's in place of Y. Now I can make that, I can simplify that, expand that. So then I would be left with negative 1.5x squared plus 30x, which also helps me with differentiating, right? I find that this is a bit easier to get the derivative of, but you can also do it this way too. So yeah, I think we're ready to differentiate. I've gone as far as I can go here. I'm just looking at my space. I'll try to fit it in on here before we move on. So to differentiate, I want to get the derivative of the area function, right? So A prime equals, what's double 1.5? Negative 3x plus, that would just be 30, x to the power of 0. So my derivative function is negative 3x plus 30. And again, to differentiate, we set that equal to 0 and then solve for x. So I can factor here. I can factor out the negative 3, or you can just move the 30 over to the other side. Any way that you get x by itself, right? Divide by negative 3, divide by negative 3, negative 30 divided by negative 3 is negative. Oh, negative and negative, sorry, would be positive. Positive 10. So x is representing also the width. Obviously, if I got a negative there, I can't have a negative width, right? So that actually leads me to my restrictions, which I can also fit in here just before I continue on the other page. So therefore, what I found out was my critical number, right? My critical number is at x equals 10. And our restrictions I was talking about here. Both, restriction is that both x and y cannot be negative. But also, if we think about that a little bit further, not just negative, but can I have a width of 0? No, right? Then you wouldn't have a shape. Can I have a length of 0? That wouldn't work, right? So negative or 0. They have to be positive values. X and Y have to actually be positive numbers. Okay, so now that I've differentiated, this is where I'm saying I don't need to do the first derivative chart, because the reason for doing it is to figuring out where I'm increasing and where I'm decreasing. But since I'm not graphing anything, that information for this particular question wouldn't be useful, right? So this is where I can jump ahead, and I'm just going to confirm and make sure that I'm trying to get a maximum. So concave up or concave down, I can confirm using the second derivative test. So I'll rewrite what my first derivative is here. So I ended up with a prime being negative 3x, that was supposed to be, plus 30. So let's get the second derivative. Negative 3, and that's it, right? Negative 3, that's it. So I had my critical number as x equaling 10. That was my critical number. So remember how you sub the value of x back into the function? So in the second derivative, if I plugged in the value of 10 whenever I saw x, well, my equation doesn't have an x. No matter what number I plug in, the answer is constant as a negative 3. So that negative 3 is less than 0, right? So if that negative 3 is less than 0, remember if I was doing the chart and I had negative, it would be concave down. So if I'm concave down, remember it looks like a frown. So if it looks like a frown, then I would have a local max. So I was trying to maximize the question. So that works. So at the value of x equals 10, I have a local max. So now I need to figure out what my other variable is, right? I've got my width. I need to figure out what my length is. So in conclusion, the dimensions are, I know that my width is equal to 10, and I already said in let x represent the width, it would be meters. And for the length here, I need to do a little bit of work. For my length, I have my equation is y equals negative 1.5x plus 30, and then sub 10 in for x. So that would be negative 15 plus 30. So I have positive 15 is the only thing that makes sense, right? 15 meters. So I have a width of 10 meters and a length of 15 meters. And if we go back up, determine the dimensions of the garden, that's all it asked me for. So I have the dimensions. The width is 10 meters and the length is 15 meters. What if though, again, this isn't part of the question, but what if it asked me to find what that max area would be for future questions? Well, what's your area formula, right? Area equals your length times your width. If this is what your maximum dimensions are, then I've got just 10 times 15. And so your maximum area would be 150, and just make sure you have the right units there, meters squared. So hopefully that one is okay. Let's look at another example here. The second one. A volume question. What is the maximum volume? So I'm maximizing here again of a cylinder. And another piece of information I have is that the total surface area is 384 pi centimeters squared. Surface area is squared, right? Volume is cubed. So let's do our drawing. So we know what the question is asking, the first bullet, to maximize the volume of the cylinder. I have to draw this freehand. I don't have a shape of a cylinder that I can click on to draw. So again, just like you in your notes, that's good enough for me. And when I'm talking about surface area and volume and I'm describing the dimensions of a cylinder, now you might have to go back and recall this, but we are looking at the radius and we are looking at the height of the cylinder. So that's where we can do our let statements. What variables are we going to use and define our variables? So again, you could use X and Y like I did in the first example, but let's say to use something other than X and Y, if I used, our radius, we just always think of R, right? So might as well use that. Let R represent the radius, obviously of the cylinder, but what are my units? Centimeters, radius in centimeters. We have H here. H is always height. Might as well use H instead of X and Y, but again, it's nothing wrong with that. Use X and Y if you would like. Let H represent the height of the cylinder in centimeters. And is there anything else? If I want to maximize volume, then I need a volume equation, right? So let V represent the volume. Now those units would be centimeters cubed, just to have that there. So we've got cubed for volume, squared for area, surface area, and centimeters for radius and height. So we already said our one equation has to be the volume equation. Again, these equations I will give to you. You'll have a worksheet, or I'll just add it right into the test question there. So the volume of a cylinder is pi r squared, the circle on the bottom, area of a circle times the height. Pi r squared times height. What do we notice here? Again, pi is not, don't think of it as a variable, because we can, that is, just think of it as a constant, a numerical value of 3.14, but I do have r, that is a variable, and I do have h, so I have two variables. So you know what I have to do if I have two variables? I need to come up with another equation. So what is that second equation going to be? So if I go back up here, we've done our volume. Again, now I have this information that the total surface area is 384 pi. We haven't used that at all. That would be my second equation, would be my surface area. So what is the surface area of a cylinder? And again, this equation will be given to you. So 2 pi r squared plus, if you remember this, 2 pi r h. But I have the answer for the total surface area. So I can put 384 pi on the left-hand side and just continue copying down the right-hand side. But I need to isolate for something, whatever you'd like. If I see I have r squared here and another r here, but I only have one h, then it might be easier to isolate for h. So if I'm isolating for h, the first thing I would do is take this 2 pi r squared and just throw it over to the other side. So I have 384 pi minus 2 pi r squared equals 2 pi r h, what's remaining on the right-hand side. And again, if I want to get h by itself, I'm multiplying here with the h. So to do the opposite, I'd have to divide by 2 pi r, divide this side by 2 pi r, divide this term by 2 pi r. So what would that leave me with here, just to clean this up? This is gone. We've got r squared divided by r, so I'd be left with an r on top. My pi's are gone and my 2's are gone. So I'd just be left with negative r. If you see that, the denominator is gone. Here my pi's are gone. I would divide 384 in half. 384 divided by 2 is 192. But the r is still in the denominator. So 192 over r minus r equals h. And what do I have to do with that? Again, if I go up to the bullets up above, my steps, I have to substitute that into the first equation. I can hopefully do that on the right-hand side here. Substitute that into number 1. I'm hoping I have the room. So again, my number 1 formula, my volume is pi r squared h. When I see h, I'm subbing in a different value. So pi r squared times, I can see that I have a fraction here, so I can do my bracket to include a numerator and a denominator. 192 over r, subtract r, close my bracket. So then what would you do maybe to clean this up a little bit? This is one term. Could do, I could expand, right? Do distributive property there. So then I'd be left with, I can do this in a couple steps here. I'd be left with 192 pi r squared over r, because you've got r times 1, minus, because you have a positive times a negative, pi r, now r squared multiplied by r to the power of 1, right? You add them, pi r cubed. But then I can clean this up a little bit because I can see the r squared at the top divided by 1r at the bottom would get rid of the r at the bottom. So then my volume formula could be 192 pi r just minus pi r cubed. I can't do anything on that other side there. Now again, think of pi, I already said this, but think of pi as a constant. It's just a number. It's not a variable. So I'm left with just one variable. Is the point I'm trying to make there is I had two variables and now I'm left with just the one variable, which is r. So now we need to differentiate, take the derivative of this formula. For that, I think I'm going to, to clear my screen and start over here. So let's rewrite that volume formula that's been simplified was 192 pi r. And the reason why I said it was constant is now when we're doing the derivative, right, we're considering pi as just a number. So when I'll differentiate on this side here, and then I'll come up on the right when I run out of room. So now when I differentiate and I get v prime, there's an exponent of 1 on this r. It would come out in front and multiply by the 192 pi again, and then r to the exponent of 0. So that's gone. Minus 3, that 3 comes out in front, multiplied by pi, and then r squared. And again, once I have my first derivative, you set it equal to 0. And what I want to do is solve for r. So how do I solve for r? Usually it's by looking to see if I can factor at all, right? So does 192 divide by 3? Is that a common term? It is, if you try it, and also pi is common. So if I pull out a 3 pi, 192 divided by 3 would be 64. I've taken out the pi, I've taken out the 3, but I would have negative r squared, right? If you're unsure, just do distributive property in your head and make sure you get back to the beginning, right? You don't want that to be a mistake there. Hopefully now you're seeing, right, that's a difference of squares. That's a perfect square, that's a perfect square, negative between them, so I can go one step farther. Square root of 64 is 8. The square root of r squared is r. We have one that's minus and one that's plus r. And then when it looks like this, I'm able to get what the r values would be. 8 minus what would get me 0 here. So that 0 multiplied by everything would be 0. 8, right? Opposite what's in the bracket. And also r would be equal to 8 plus negative 8 to get 0. So negative 8 and positive 8. So again, I just changed colors just so it can stand out here. So therefore my critical numbers are at r equals, and again, do it in numerical order from least to greatest. But we said r represented what? R represents the radius in centimeters. We actually didn't list what the restrictions were. So the restrictions here would be the same thing, that they would all have to be positive numbers, no negative numbers, and not 0 as well. I can't have a 0 radius and still have a cylinder. I can't have a 0 height and still have a cylinder, right? So if this is a radius of negative 8 here, just to point out, that doesn't make sense. So really I'm just going to use the critical number of a radius of 8. And what I'm trying to do is maximize my volume. So I'm going to use, I'll write that out here, the second derivative test to confirm. Using concavity, so a second derivative test to confirm that I have a maximum. So where's my first derivative? 192 pi. You don't really have to write it out again, depending on where it is on your page though. If I'm going to go look for it to try to compare that with your second derivative, because let's say you made a mistake there and from there you did the second derivative properly, it might be a little bit hard for me to see how you got that second derivative if the first derivative isn't right above it. So just for your own good, especially for mistakes. Now there's no R value here, right? So the derivative of 192 pi, that's just a number. Pretend it was just 192, that would be 0, right? Then this 2 comes in front, would be negative 6 pi r to the exponent of 1. So really it's just negative 6 pi r, the second derivative. So then what we always do is we plug in our critical. So if I need to list that, plug critical number into your second derivative. So add a value of 8 when I see R, I put 8 in its place. That's going to be negative 48 pi, which equals, if you do it on your calculator, I've got my answer here. I want to see, did I use 3.14 or pi? Negative 6, negative 48. Might have used pi. You end up with negative 150.796. So negative 150.8, let's say. And that would be, so all we care about there is that it's a negative number, really, right? That it's less than 0. So because it's less than 0, I'm going concave down with a frown. Concave down with a frown, which means I have a max. So that confirms that I have a max, right? So therefore I do have a maximum at a radius of positive 8. So now I can just plug that, what is the maximum volume? So then I need to plug that radius of 8 into my volume formula in conclusion then, right? Hopefully I can fit that all underneath here. I guess I'll start over here and kind of work my way to take up all the space here. So in conclusion, my R is 8 centimeters to figure out the volume. My volume formula, again, is pi r squared h. So I've got that my R is 8, but I need to know what my height is then, right? I have my a formula for height. It's not here, but again, my formula for height was, you remember, 192 divided by r in terms of r minus r. So I can use that and solve for what my height would be. So 192 divided by 8, subtract 8. Does 192 divide by 8 nicely? You get 24 minus 8. So I get a value of 16 centimeters for the height. Now I can figure out what the volume is. Pi, or 3.14 times 8 squared times 16. So again, you do that. So 64 times 16 times pi, or times 3.14. And I have a value of 3,215. Decimal 4, and make sure to put your units centimeters cubed. So again, therefore my maximum Go back and read the question. What is the maximum volume of a cylinder if I have a surface area of that 384 pi centimeters squared? So therefore, my max volume would be 3,215.4 centimeters cubed. Okay, if you can see in this lesson, we have a third question, number 3 there. Give it a read through, and we will do that in a separate video.